Hi, I'm Becky Peltz, and I am going to take you through a learning module here on network routing and transport. So this is an important part of moving data across a network, and we see it every day when we work with the internet. So we're going to learn about how IP, TCP, and UDP protocols move data between a sender and receiver on a network. Well, look at these objectives: understanding network models, grasping core network mechanics, looking at the internet layer with an IP protocol, the transport layer with TCP and UDP protocols. We'll identify transport protocol use cases and security issues. And finally, we'll do a code demo where we look at error checking using the checksum algorithm. Starting with our foundation, network models. We have two models, the OSI, which is Open Systems Interconnection, TCP/IP, which is Transmission Control Protocol, and Internet Protocol. And we're going to look first on the left at OSI. And what you see is seven sections, seven layers starting with the application layer and working down to the physical layer. The OSI is a model that is theoretical, but we'll see that the TCP/IP model is very related to it. And by calling out these layers, it helps developers and admin understand where data might be in a network, whether they're trying to write applications or just solve error problems that they see on the network. So the application layer and presentation and section are going to take care of gathering data from the user and then encrypting it if necessary, preparing it so that it is ready to be moved. And then we get to the transport and network layer, and you will see that these are sort of replicated over here on the right in the TCP/IP model. But these are the layers, the transport that's going to actually move the data and the network that's going to kind of know where to move the data. And then the data link, which kind of prepares this bulk of data that's been sent down from application and gets it ready so that it can be sent to the physical link where it would, physical layer where it would actually move out of the computer into cables. So that's our theoretical model that gives you a kind of look at the big picture. The actual model that the internet uses is the TCP/IP, and many networks do. Local area networks, wide area networks. It is a very well-used model that's been implemented for networks. And if you look at this across the left to right, you can see that in TCP/IP, the three layers of OSI are kind of bundled as application. We still have a transport layer, and we'll be seeing TCP and UDP implemented there. And then we have the network layer, which is called internet over on the TCP/IP side, where we have the IP protocol. And then data link and physical are bundled into link. So really, TCP/IP model is the model that we would implement and what you would experience if you're working on the internet. Well, let's just look at each layer of the TCP/IP model. So at the application, we've got the HTTP protocol, which is what creates web pages and moves web pages around. And there, at each level, we're going to see that header data gets added. Now, our main concern will be transport and internet, but with HTTP, we get what's called messages on the headers. TCP and UDP, you're going to see segments for TCP and datagrams for UDP. The IP layer, we'll see packets, and we'll at the MAC layer, we'll see headers and trailers, and that makes up a frame that gets it ready to actually be sent through the physical device that is going to pass the data out onto the cables. So we're going to look a lot more at this segment and datagram data as well as packets as we look into how we actually send and receive data. And you can see that it's a two-way saying here, because when you transmit, you're starting an application and you're modifying data down to the link layer so that it can go out into the physical world. And then when you receive, so that would be like sending a request. And then when the receiver gets that, they're going to experience it coming in through the physical, up through the internet transport application until it gets to the receiver. Here's some um, here's some language here's that can help you to understand some of what's going on in this movement of data. So we have a request from the sender, and we're pretty probably familiar with the idea of a client server model where the client is running an application and it wants to make a request to get some data. And so the request comes from the sender. Starting at the application layer, a request is generated. From application, it'll go through the layers that turn it into something physical. That's called the encapsulation, making it available and having addresses so that it can move across the internet. And as it gets to the server now needs to decapsulate it, so take it apart, starting at the link layer, the physical layer, and then slowly building up to where the application layer of the server can do something with it. And then it goes back through that whole breakdown process, getting encapsulated and sending it across the network, where then the client can decapsulate what the server has returned. So if you can picture that full round trip in the way that these client and server are each both starting with application and ending with a physical set of bytes, or taking in a physical set of bytes and generating an application or generating data that could be used in an application. That's what we're seeing in this diagram. So let's take a look at the internet layer. That is the lower layer if we think of starting at the top as application and moving down to physical. Internet is lower than transport. So what does the IP do? IP is the IP Internet Protocol. And what we're looking at here is a packet. So IP is its main responsibility is sending this is knowing about the source and destination addresses so that it can send this to find the best path to get this packet to the destination address. So it determines the best path. It uses packet forwarding as a function to get there. And if it's sending data to a server that is on the same network as the client, it actually doesn't need to go to a router. But generally, if it's sending it to a different IP address, it needs to go through a router. So it would be sending it through that router. And then it does error checking. So we see this header checksum, and we'll see a lot more about checksums. This is like an algorithm that helps to verify the integrity of the data. So that's our IP packet. I'm showing IPv4 packet. There's also IPv6 for the more extended addresses, but the IPv4 is shown here. And this is a very common form of internet transport. And then when we get to the transport layer, so now we're going to look at two protocols, TCP versus UDP, because there are two available, but they differ quite a bit. And the big difference breaks down into reliability versus speed. So let's take a look at that. So TCP, Transmission Control Protocol, what makes it reliable? And there are three things that TCP does. It creates connections by way of a three-way handshake. You'll see what that looks like. And then packet sequencing. And that's where it keeps track, it numerically orders packets that it receives. Now, it turns packets into what it calls segments, but it keeps that ordering, and it will complain if it doesn't, if the orders get out of sequence or something is missing. We'll see that. And then we want to be able to trigger a resubmit for lost data. For some reason, it recognizes that it's not getting a packet, it can trigger a resubmit from the sender. So I tried to make a image of what does a three-way handshake look like, and I came up with something on AI that is not really very helpful. I mean, we see two hands and then some various body parts that might be feet even. Um, but these words, ACK, SYNAC, ACK, these are something that if you work on networks, you're going to know really well. ACK stands for acknowledge. SYNAC means synchronize and acknowledge. And then ACK again, acknowledge. And this is how the three-way handshake works. But this is not a great look at how it actually works in our computers. So this diagram helps to see how this handshake works. The idea is it wants to form a connection, and that's really important. And we're forming a connection across probably two physical computers that are not on the same network and that are very wide, could be very far away from each other. So rather than just randomly sending things back and forth, this connection can help to maintain integrity of the entire set of data. So the client sends out a SYN, sync. So that message is sent to so that if we think of the client as the transmitter, the server is the receiver, we're transmitting SYN to the server saying, can I sync with you? And when the server gets that, it sends back SYN-ACK, which says, I heard your sync and I acknowledge it. And when the client gets that, it sends back an ACK acknowledging, okay, I acknowledge that we can sync. So these are the first steps. This is what initiates that connection. And then we're going to see a little bit about what happens during that. But at the end, we have some other signals that can go across. Fin when we're done, finish, and RST when we want to reset for some reason. And usually it's because there's been a problem. All right, let's look at the TCP connection data flow, where we have a client sending data to a server. Client is the sender, server is the receiver. So client transmit, server receive. And what you see here in this is we're sending our SYN, SYNAC, ACK, and this gets counted here on the server. The ACK is what the server maintains for sequencing. So we start with the SYN 1000, we add 1 for the ACK, and then the client takes the acknowledgement value, and that becomes the sequence on the client. So both sides are actually keeping track of how much data and the sequence numbers. And then here on the client, we send ABC, 3 characters. So on the server, our ACK becomes 104, and when that gets back to the client, then it gets recorded in the client sequence. And then we add DEFG, and now we're up to 108. And then we save that on the server, I'm sorry, on the client, and as a sequence number. And then the server sends the client an ACK. That gets recorded on the server side as an ACK. And then this server sends FIN-ACK, and then that gets recorded down here as a sequence. So we're maintaining the numbers, the sequence numbers on the client in the seek field, and we're maintaining them on the server on the ACK field. But both sides are responsible for keeping that sequence number. And if for some reason data doesn't make it across, you will see that there is a resolution for that by the server sending back ACKs that have already been sent before. So this is how this flow takes place. So this is what, I'm going to close this little picture here. This is what a TCP header looks like, and then we have the data down at the bottom. So this is what you call a segment, and this is in the transport layer for using the TCP protocol. And we could just call out a couple of things. You can see some of those little fin, some of the things that might get some bits that might get set. But the important things for right now are we have a sequence number, and that's what's going to keep our data in order. So when it gets to the application layer, it's all in order and it can be processed by the application. The checksum, that's going to be a calculation. When the packet is made, it just runs an algorithm that takes all this data and turns it into a single number. That's a checksum, and that can be verified. We can just recalculate and make sure it matches the checksum. And then we have the data being transmitted. So all of that is what makes up the segment. Now, what can happen is we do not allow data loss. We don't want data loss in the DCP with the DCP protocol. If there's no missing segments, we just send back that ACK. If there's a sequence out of order, what's done is there's two ACKs sent with the same sequence number. That signals to the transmitter, get a new segment. If we have corrupt data, like the checksum determines that there's a problem with the data, we can send a retransmission timeout and we can get a new segment. So that's how we can deal with preventing data loss. Now, with UDP, user datagram protocol, what makes it simple and fast? So we're going to take a look at that. So there's two protocols at the transport layer. We've seen the reliable packet or segment oriented TCP. Now we're looking at UDP. And this is a connectionless communication, often called fire and forget. So and we can compare here TCP to UDP and see here we've taken the time to set up a connection with TCP, and a lot of data is moving on TCP. So we have a SYN ACK to get the connection going. But notice with UDP, our client makes a request and then the server just starts responding over and over. There's no attempt to coordinate between these two, client and server. We just kind of, in UDP, dump everything back. So that's that's a very different way of looking at it. But it also saves a lot of work. Yeah, there's a lot of extra, say, time spent with doing the connection and keeping track of the sequence. And with UDP, you don't have that. So you do get much faster results. And the datagram, which instead of a segment here, we have a datagram, is a lot simpler. So there's less data to keep track of. There's still a checksum. There's still this datagram that you want to make sure is not corrupted. But there's no connection, no error checking. Datagrams may be out of order, and that's not a problem if you're using UDP. There's less overhead data in the header, so this is smaller. That's going to make it move faster. And error checking still occurs with the checksum. But the key is that it's faster. And so what we have to look at now is why would we use TCP versus UDP? So we'll look at a comparison on both use cases and security and when to use each protocol. So TCP, that is the main for web browsing, email, file transfer, the main protocol that's used. And remote login, cloud computing. So TCP is used a lot. Now, UDP is better for things that are time sensitive. If you need a weather report, which changes a lot. If you're doing gaming and you're sending lots of data back and forth, or video, lots of data being sent, you're going to probably want to use UDP because it's going to go faster. You're not necessarily going to care if things are out of order or there's just a tiny glitch. Your user might not even notice it. Voice over IP. So again, lots of data when you're talking about audio. And then DNS lookups, so domain name servers. This is a huge thing, is, the translation of a, www.google.com into 1.2.3.4. That's the domain name server, changing that name into a URL, into the numbers that make up an IP address. And NTP, so that's our time protocol, getting requests for time. Obviously, you don't need to spend a lot of time doing connection if you just want to get the time from a server. So those are the use cases. And then the security considerations kind of follow on those. With TCP, session hijacking and injection. So what can happen is, um, hackers can figure out, can kind of guess or figure out a certain sequence number in a long transmission, back and forth, and they can inject in that to that sequence, and they can actually inject over and over and over again and cause a denial of service. So basically, everything is kind of locked up because of overload there. And that's like a SYN flood attack. So just sending a sync at a server over and over again, that can generate a lockup, like a denial of service. There's no default encryption or authentication with TCP. So obviously data, if someone got a hold of a packet, might be able to look into that. Now, what should happen is that the application layer would take care of encryption so that the data that you get down at the transport layer doesn't have it. But it's still, there's not going to be any additional there. Now, UDP can get IP spoofing and lack of authentication. So this is where you can just, similar to what goes on with session hijacking, just kind of have a hacker break in and, take over. You can also have UDP flood attacks, which is like sending, because there's so much data there, just sending all that data at a server, and it could result in a denial of service. Amplification attacks, so distributed denial of service. You can just have tons of data flowing at a server, or tons of UDP requests going at a server, and no data integrity. So you can have lost packets basically. So it's not checking like the way that TCP does that makes sure that every packet is coming and it's in order and it's kind of validated on both the sender and receiver side. Instead, you can just lose packets like that. So let's do an error checking simulation. Let's take a look. Actually, we're going to actually, it's not even a simulation. We're going to actually run a real checksum algorithm to detect data corruption and take a look at what that's like. But before I do that, I want to call out this tool, Wireshark. It's free, it's open source. You can download it, very easy to hook up to your network. And you can start to see the flow of traffic on your network with the different protocols. And you can click on these rows and actually examine the packets. So if you want to like get more proficient at looking at network data, this is a good way to do it. And this is used by developers who are creating network applications as well as admins who are looking for problems and trying to figure out why they're coming about. This is a really great tool. You can download it for free from the internet. But let's take a look at the checksum. So a checksum, there's a number of places on where fingerprints of data are created, and you can learn about those when you're doing file transfers and application downloads. The checksum is a way to create a fingerprint. So basically take all your data, run it through an algorithm, you get a single number, and that number describes your data, and it can be saved. And anytime you run that algorithm on your data and your header, you should get the same number. And what's the algorithm that's used is the 16-bit ones complement, or sometimes called the internet algorithm. And I've got some basic steps here. So what happens is you pass in some bytes. So just, like a byte, a string turned into bytes, or a byte array. And what you're going to get back is a 16-bit checksum as an integer. But basically, you're just going to be counting in here, but you're going to be doing some flipping of bits. So you initialize the sum to 0, you process the data into 16-bit 2-byte chunks, and then you add the 16-bit word to the running sum. When you do this, you can get carryover. So in other words, your sum ends up being greater than the 16-bit word can hold. And so you can do folding, as they call it, to the carryover bits to add them back into the 16 bits. So when you're all done, you have 16 bits. And then you take the ones complement and then invert all the bits. So ones complement is like flipping from 0 to 1, 1 to 0. It's like a subtraction in bits. And then you just invert all the bits. And that gives you the checksum. We'll take a look at the code for this. So if you're familiar with Python, this particular algorithm here is written in Python, and I'm running it in PyCharm. But if you're not familiar, Python is a relatively simple language to look at and kind of see what's going on. And so we're going to look at it in Python, but it's could be this kind of algorithm is implemented in many languages. So basically, we're going to calculate a checksum by passing in some bytes, and we're going to return an integer. Start out by initializing that checksum value, and then we'll take that data that we passed in, and we'll step through it 2 bytes at a time. Okay, so remember that a byte is 8 bits, so that gives us our 16 bits. And then we just iterate through. And for each chunk of data, we do if it we take the low end and the high end and we add them together to create the word. And then we pad any if we so either we're adding words or we're padding it with zeros, padding the end of it with zeros. And then we add that word to the checksum. And then while the checksum is greater than 16 bits, so we need to handle carryover. That's when the sum adds up to more than will fit in 16 bits. And we just take the checksum and we make sure that we take the first 16 bits and then we get anything past that and add it to it. So that's the carryover. And then we take the ones complement and invert all of the bits there. And then we XOR it to make sure it stays at 16 bits. So, oh, we actually flip all the 16 bits. So then we return that. Now this application also has a verified checksum, so it's just going to take a string and then calculate its checksum and compare it to the received checksum. So if we're expecting a certain checksum, we pass in the bytes and it calculates the same number, then they match. Otherwise, they don't match and there's an error. So we have a demo here that will take this, uh, the B for the string means that we sent in bytes, hello network, calculate the checksum, get the answer back, call decode on it. We should see our original data. I'm showing the type of the checksum here just to verify it's an int. And then we show it in hex and int and indicate whether the verify passes. So we call the verify on the data in the checksum. If passes, we're good. No errors. Then just to throw it at the wall, we flip 1 bit in there. So we take our data and turn it into a byte array. So now we've an array and we flip the first bit. So we just change that. So now we've corrupted it. And then we can print that out, what that looks like corrupted now, what the string would look like. And then we call the verify checksum. And guess what? I'm not going to give it away. We'll run this. And I'm just going to run this checksum. And here's the result. So we sent in hello network. We got back an integer. That's our 19,300. And we show it in hex. It's verified. Now look at our corrupted data. We flipped that first bit and now H is I. And we sent that in and we got the checksum back as false. You can see that our new number was 19,044 instead of 19,300. And they differ, so we have corrupted data. And this is the algorithm that gets run on all those segments, packets all over the internet. All right. Let's go back and let's summarize what we've learned here. So we rely on the TCP/IP model for most networks. The IP Internet Protocol is the internet layer responsible for routing packets to destination IP addresses. TCP, or the Transmission Control Protocol, and UDP, User Datagram Protocol, are transport layer protocols. TCP is more reliable because it connects receiver and sender to guarantee that all segments are delivered. UDP is faster, but it may lose data. TCP and UDP rely on checksums to ensure data and headers are not corrupt. TCP is best for applications that rely on data integrity, but UDP is good for time-sensitive data like streaming videos and video games. Both TCP and UDP can run into security issues like denial of service, DOS. Checksums are used for error checking. So this concludes our module on working with the internet and transport layers. And I hope this will help you move forward. Edit. Okay, let's just fix this now. I can just do this thing here. And I can do, let's see. PC pair two. Okay, I'm gonna go here, here. All right, let's summarize what we've learned in this module. We rely on the TCP/IP model for most networks. IP, Internet Protocol, is the internet layer and is responsible for routing packets to destination addresses. TCP, Transmission Control Protocol, and UDP, User Datagram Protocol, are transport layer protocols. TCP is more reliable because it connects the receiver and sender to guarantee that all segments are delivered and in order. UDP is faster, but it may lose data. TCP and UDP rely on checksums to ensure data integrity and headers are not corrupt. TCP is best for applications that rely on data integrity, but UDP is good for time-sensitive data like streaming videos and video games. Both TCP and UDP can run into security issues like denial of service. Checksums are used for error checking. All right, well, I hope that sums it up, and thank you.